Hi everyone, welcome back to the FRC training video series. Last video we talked about how pneumatics works, and today we're going to be reviewing and learning some programming stuff by examining the code I wrote to run the simple pneumatics system I showcased before. Reminder to have the quiz open as you watch the video, which is linked in the description. First, let's review command-based structure. If you recall, command-based programming is based around subsystems and commands. Subsystems compose the individual parts of a robot, like pneumatics devices, motors, or sensors, and define how we can use them in methods. Commands define the specific actions that the robot performs, and take advantage of the methods used by the subsystem. Something important to know about commands is that although we can run multiple commands at the same time, we can't run multiple commands that use the same subsystem at the same time. If we try to do this, one of the commands will stop depending on what we have specified in the program. Now let's dive into the code. First, let's take a look at our pneumatic subsystem. This subsystem is designed for us to be able to perform simple actions with one or more double solenoids. The first thing to note is the nested constants class. Inside here, we have an array of double solenoids. And we know this is an array because of the square brackets here. In this case, having an array of double solenoids means we can control multiple double solenoids with a single instance of our subsystem. Next, we have the constructor, which specifies what happens when we create an instance of our subsystem, as well as takes in any parameters that we may need to get our subsystem to work. The parameters in this case is an object constants of type constants with a capital C. This wording is a bit confusing, but if we look back to our nested constants class right above this, we can see that it's essentially asking for us to create an object of this and define the constants inside of it. This can be seen being done later in the constants file. Next, let's look at the code inside of the constructor. Here we can see it sets M solenoids, which is a private variable that is also an array of solenoids. This allows us to access our array of solenoids locally within our subsystem. After that, we have this for statement, which roughly translates to for each double solenoid, which in this case we call some arbitrary variable s, in m underscore solenoids, which is our array of double solenoids. It will set the value of each solenoid in the array to reverse. So what this constructor does is 1. Set m solenoids, which is our local array of solenoids, equal to what the user has inputted as the parameter, and 2. Set all the solenoids to reverse, which we can assume is the retracted setting of our piston. Then let's move on to the methods defined here. These methods are pretty simple because all they do is take the methods that are already defined by our libraries, which we can see up here, and make them methods that are native to the subsystem, or methods that we can use with instances of our subsystem. If we read the code, all it's saying here is that if we use the toggle method, it will toggle each solenoid in our array. Same thing below, if we use the set method with some input direction, it will set each solenoid to that input direction. If we hover over these methods, we can also see that they are methods from the double solenoid library, which has already been provided for us, and that we're just adapting them for the subsystem by a method of the same name. This teaches us something important, which is that we have to specifically define any method that we want to use in any given subsystem, even if it seems almost redundant like it does here. Next, let's examine the constants file. This is where we will create an instance of the nested constants class within our pneumatic subsystem to create the solenoids that we're going to use. Here we can see that we create a new pneumatic subsystem.constants object, which is basically this right here. Then within that object, we initialize our array of double solenoids and add a new double solenoid with these parameters. we can see what these mean by hovering over our constructor here. Module 10, and for solenoids, module just refers to CAN ID, module type of rev PH, or the rev pneumatics hub, and forward and reverse channels, which refers to the port that the solenoids are plugged into on the pneumatics hub. Okay, now that our constants are ready, let's take a look at robot container. So the first thing that we see is that we instantiate pneumatic subsystem, Xbox controller, and compressor into our objects. For our M piston, we can use constants.pneumatic constants as the parameter, which we can see if we go back to the constants file, refers to what we wrote in the constants file. For Xbox controller, we simply refer to the port that the controller is plugged into, which is always going to be 0, unless we have other controllers also plugged in. Then we also have to create a compressor, since we are working with pneumatics. Now, something to note is that the reason why we don't include the compressor in our pneumatic subsystem is because our robot could have multiple instances of pneumatic subsystem, or we could even program more subsystems that also use pneumatics. And that would mean that every time we make a pneumatic subsystem, we would make a new compressor, which we don't want because there's only one compressor that powers the entire pneumatics network for the robot. So we have to create it separately here. Okay, so now that we've created the subsystems, we can take a look at the button bindings. First, we make 3 new joystick buttons for retracting, extending, and toggling the compressor, with their bindings specified here. Then we configure these bindings in the code right below. Here we say that when this retract button is pressed, we run an instant command, which is a default command type that just runs the code specified there immediately, that just extends the piston. We use this notation with the parentheses and an arrow, since the parameter here is what is called a runnable interface. So remember to put this whenever you hover over the constructor and see that's asking for an object of type runnable. The actual name for this is lambda notation, but it's somewhat advanced, so I won't be covering the specifics. However, we can see that there's also another parameter here that is a subsystem, or rather multiple subsystems that you can input. This is the requirement of the command that we have to specify, or requirements. As I explained before, although multiple commands can run at the same time, only one command can be run by a single subsystem at one time. So it's important that we specify this add requirements field so that we don't tell our robot to do 2 contradicting actions at the same time. Actually though, in our case, since it's simply an instant command and only runs for a fraction of a second, it doesn't really matter if we put in the requirements, as there's a negligible window of time where our command actually controls the subsystem, so there's essentially no way for another command to interfere, but it's still good practice to write it in. But if we had a more complex command, like say a command that moved the piston out for a few seconds and then retracted it, we would definitely need to specify the required subsystem, since the command takes a decent amount of time to execute. Moving on, our extend button is essentially the same thing, but set to the other direction. Next, our toggle compressor button is binded to a conditional command. So this is something that we haven't seen before, but it's still somewhat intuitive. It takes in 2 commands, labeled onTrue and onFalse, as you can see here, as well as a Boolean supplier or condition, which is basically the same as a Boolean, but we have to use this bracket notation again. The way it works is that if the condition that we specify is true, it will run the first command. But if the condition we specify here is false, then it will run the second command. So if our compressor is enabled, it will disable it. But if our compressor is disabled, it will enable it. With that, we've gone through all the pneumatics code. But there's still a few important things that we have to cover, which is the rest of the included command types, command groups, and trigger or button bindings. For command types, we can refer to this page on the WPI-lib documentation that describes the several types of included commands that we can take advantage of. There are lots of useful ones here, but the ones we use most often are instant command and run command. However, as you can see, the conditional command that we used earlier is here. Instant command we've used a lot before, but as a recap, it just runs whatever code is specified immediately. Run command repeatedly runs whatever code is specified, so we often use it for the default command. As an example here, we can see we use a run command as the default command for our drive-based subsystem, which makes sense as we always want to be mapping the controller input to movement on the drive base. I recommend checking the rest of these out on your own, but don't feel pressured to memorize all of them because we can always access this documentation. Next, let's learn about command groups. Command groups allow us to do more complex things with commands, like run them in sequence, run them at the same time, and many more things. I've linked a page to a list of all of them in the description, but the most important ones are sequential command group and parallel command group. Sequential command group allows us to run any amount of commands in sequential order, and will finish once the last command finishes. Parallel command group allows us to run multiple commands at once, and will also finish once all of the commands finish. We can also nest command groups inside command groups. So if we wanted to drive to a certain point and then lift an arm and open a claw at the same time, we could write something like this. Finally, we have trigger and button bindings. Once again, a link to this documentation is in the description. When we use a button on the Xbox controller that is not the D-pad or back trigger buttons, they are considered joystick buttons, whereas when we use the D-pad or back trigger buttons, they are considered triggers, or rather, we create them as trigger objects. When to use which one of these can be a bit confusing, so I'll cover them later, but for now, just know that they're different. When we are binding buttons, we want to use the binding that corresponds to the type of button we're using. If we refer to the documentation, if we want to use a when active or when press command, which are essentially the same, with our joystick button, we have to always take the second binding action that's listed. In other words, the binding after the slash. This is because the first binding refers to the binding that we use for triggers, whereas the second binding refers to the binding we use for buttons, including joystick buttons. Although this isn't really explicitly said on the website, so you kind of have to memorize it. We can also figure this out though by just going into the code and interchanging the two bindings and hovering over each binding to see whether it's meant for a trigger or button. You can see that right here. There are some situations where the bindings are interchangeable, so you can use a trigger binding with a button binding and vice versa, but it's best to keep it consistent. That's all for today. I hope this video was helpful, and once again, please ask me if you have any questions. Thank you.